All right, so today we're talking about all of chapter 16, which has to do with entropy and Gibbs free energy. But the first thing that I need to start with is spontaneity. In chemistry, a spontaneous process is that it is a process that occurs without outside intervention. That means you don't have to mess with the temperature, you don't have to mess with the pressure. Left to its own devices, it happens on its own. So if A and B on their own combine to form C, which is a pretty good trick, if that is spontaneous, that means nothing need be added to it for it to work. Now, this can be a fast process or a slow process. The fast or slow will be taken care of in chapter 12 when we talk about kinetics. That's the rate of the reaction. We're just talking about whether it is thermodynamically favored and the universe will let it happen. That is spontaneous. So here is a process that we're talking about. Both of these things are spontaneous, but the rates are far different. The combustion of pentane happens very rapidly. You add the activation energy and boom, it goes. All right, now the process of a diamond being changed to graphite is also a spontaneous process. So when they say a diamond lasts forever, they're lying. Right this moment, every diamond you own, do you own lots? Multiples. All your diamonds are slowly changing to graphite, which is pencil lead. That's also a spontaneous process. The difference is the rate of the reaction. Okay, if A plus B yields C, and that is a spontaneous process, then the reverse reaction C, decomposing to A plus B, is not spontaneous. All right, let's talk about the laws of thermodynamics. The 0th law of thermodynamics is that two systems will come to thermal equilibrium. That would be the fat Russian and the snowbank. The first law of thermodynamics is the conservation of energy. The second law of thermodynamics is the disorder of the universe is constantly increasing. I am not talking about the universe that contains the Milky Way. I'm talking about the universe that is composed of the system and the surroundings. So the disorder of the universe is constantly increasing. The third law of thermodynamics says that the entropy of a perfect crystal at 0 degrees K, absolute zero, is zero. Please remind me to go back and explain that once I get done with this bit. All right, in Chem 1, we talked about entropy. Entropy has the abbreviation of S. That's a state function. You remember a state function means it doesn't matter the pathway. The end result will be the same no matter how you go about getting there. It's a state function which is a measure of the randomness or disorder of a system. Okay, do you remember that definition from Chem 1? Entropy is the measure of the disorder of a system. How many of you have your own dedicated space within your house, otherwise known as your room? Okay. Now, if I am correct, you are like the universe, and you are lazy. You would like to maintain a low energy level. Now, you could go to the Container Store, spend $1 bazillion and buy all those little inserts for your dresser. The one that gets me is that little sock thing. Like, you have a sock drawer and then you divide it into like 24 little segments, and you're supposed to take your socks and roll them up into socks rolls and then bundles, and then put them in like blue sock, white sock, white. Okay, that takes a lot of energy. Who wants to do that? And then you're supposed to fold your t-shirts into little bundles of shirt and put them in this proper place. That takes a lot of energy. Nobody wants to do that. You can do like my son does. He has his own apartment, and what he does is he does his laundry, bonus, but then he takes it out of the dryer and throws it in his bedroom. He lives alone, right? Low energy maintenance there. The entropy of his room is way higher than the entropy of somebody who has those little sock divider things. It takes him no energy at all to say, ooh, there we go. He wears a clean Keep Austin Weird t-shirt, right? It's clean, it's been through the washer dryer. It just hasn't been pulled into a t-shirt packet and put away. He is increasing the disorder of the universe. Okay, now the high school, the Chem 2 equivalent of the entropy definition is this. It's a measure of the probability of the number of arrangements available to a system. What are you talking about? Okay, back to the laundry situation. When you have those little dividers for your sock, there's only one arrangement, only one place. Everything has its place in that system, right? The socks go right here with the other blue socks. The entropy is very low because there's only one possible arrangement for those socks. Now, in the Keep Austin Weird situation, there are many, many different places those socks can be. They could be on the floor, they could be on the ceiling fan, they could be in the closet, they could be on the TV, correct? The entropy of that system is much higher because there are many probable places for the socks in question to be. Now do you get it?
Yeah.
All right, thanks. Okay, so if we're talking about a system, and we would like to know the entropy of the system is the final minus the initial. That's still products minus reactants. Products minus reactants again. Now, if you've determined that the change in entropy of the system is positive, that's an increase in entropy, and that is generally spontaneous because the disorder of the universe is constantly increasing. Increase in entropy, increase in disorder, the universe wants that to happen. If the change in entropy of the system is negative, that's a decrease in entropy, that process is generally not spontaneous. Please note the terms generally. That's because there are exceptions to this rule. And something we need to go backtrack and revisit is this. If the enthalpy, the heat content of a reaction is negative, that would be an exothermic reaction, that is generally spontaneous. If the heat content of a reaction is positive, that's endothermic, that's generally non-spontaneous. Now, I can think of a delta H a delta H at standard conditions, that's an endothermic that's spontaneous all the time. Generally not spontaneous, sorry. And endothermic generally not spontaneous. One example that is spontaneous is the melting of ice. Melting of ice is endothermic, yet it happens spontaneously at room temperature. Okay, so exothermic, generally spontaneous, endothermic, generally non-spontaneous. You're going to be asked 1,000 times to determine whether the entropy of a reaction is increased or decreased. Here are some guidelines for you. A change in state from a solid liquid to a gas is an increase in entropy. If you think about a solid, let's say a metal, let's say a piece of copper, there are only so many places for the copper atoms to be in that piece of metal. They're vibrating around a fixed position. Fixed means they can't move. If you melt the copper has more freedom of movement, so it has more places for it to be, more numbers of arrangements, and then by the time it gets to the gaseous state, it's randomly rocketing around. It has a lot of places it could be. If you increase the temperature from 10 to 100 degrees C, you increase the kinetic energy, you increase the rate of its movement, its velocity. It has more places to be because it's going really fast. Come on this way. When a particle dissolves, you release the atoms from its, thank you, this one. Okay. You release the atoms from its crystalline structure. You hydrate them, they can slide around. When the number of gas particles increase, because gas has such a high entropy, if you increase the number of moles of gas, the entropy increases. When the molecular complexity increases, so does the entropy. This can only rotate around this fixed position, but this can be like that, or it could be like that, or it could be like that. There are more places. So if you increase the complexity, you increase the number, the entropy. The more atoms you have, the more complex it is, therefore the more entropy you have. Predict the sign of entropy change for each of the following processes. Solid sugar is added to water to form solution. You dissolved it, so the entropy increases. Iodine vapor, that's a gas, condenses to form crystal, not condenses, it deposits on a cold surface to form crystals, which is a solid. So that is a huge decrease in entropy. Which of the following has the largest increase in entropy? CO2 solid subliming to gas, that's pretty big. Hydrogen gas plus chlorine gas, 1 mole of each, makes 2 moles of hydrogen chloride gas. That's a push. Those are equal. KNO3, a liquid KNO3 going to solid KNO3, that's a decrease. And the very highly complex diamond becomes sheets of graphite. That is increase in entropy, but not a huge one. Now you got thermodynamic data charts. Find yours. It is on 8.5 by 14 paper. It's a long one. That would be it. Now, heretofore, thank you very much. You've only used the delta H values. Now we're going to look at the S values. First of all, the first thing you need to notice is the value is S. Not delta S, it's S. There are absolute entropy values. The second thing you need to notice and highlight this, I'll tell you what, if you dated this wrong, right off the bat. First of all, S is not delta, it's S. There's an absolute value. Look at the difference between delta H and S. This is in kilojoules, this is in joules. Be careful.
What is K mole?
Per degrees Kelvin per mole. So you're going to pay attention to that. To calculate entropy from the standard tables, you're going to do the products minus the reactants, and we're going to do one right here. Calculate the entropy change at 25 degrees C in joules per Kelvin for this reaction. Please also note that there are values for elements in entropy. So it's still products minus reactants. There are 2 SO3s, so that would be 2 times 256.6 minus the products, 2 SO2. SO2 is 248.1 plus the 1 mole of oxygen is 205.3. And this is what we come out with, negative 188.3 joules per Kelvin per mole. Now, that makes sense because we have 3 moles of gas here, and we have 1 mole of gas product, so the entropy of the system should be decreasing, which is a negative number, so we know that everything is okay.
Would you have to write mole after the K?
No. No. It's kind of like the mole is silent. We do that sometimes. If you did it, you would be absolutely correct. Okay, from here, we're sliding on to the,
You can see it again, but for the magnets, all they have like those little displays in the bars, kind of, you don't usually put the displays or just.
yep,
Okay.
thanks. Okay, now we're moving on to the last, the big dog thermodynamic. Gibbs free energy. Mr. Gibbs found a way to marry enthalpy and entropy to predict whether a reaction occurring at a constant temperature and pressure will be spontaneous. It's called Gibbs free energy, and here is his formula. The change in Gibbs free energy, and you need to define Gibbs free energy, is the amount of energy available to do work. The amount of energy available to do work is equal to the enthalpy minus the change in enthalpy minus the temperature in Kelvin times the change in entropy when it's under standard conditions. We add that ought sign. That, remember, that's 1 atm, 25 degrees C, and 1 molar. So far, so good. Now, why don't you skip down here for a second. Delta G overrules delta H and S. It's the ultimate decider. Of spontaneity. If delta G is negative, that reaction is spontaneous in the forward direction. If delta G is 0, the reaction is at equilibrium. You don't know that, but it's something at its at equilibrium. The rate of the forward is equal to the rate of the reverse, which is something we'll get into. So if it's negative, the reaction is spontaneous in the forward direction. If it's 0, it's at equilibrium. If it's positive, it is not spontaneous in the forward direction, but it is in the reverse. Delta G is a state function, just like delta H and delta S. That means it's still products minus reactants. And if you look at your thermodynamic chart, looking at it, your thermodynamic chart, we also have delta G listed. The units are the same as delta H, kilojoules per mole. And once again, like delta H, all elements have a value of 0. All elements have a value of 0. Are you going to forget that? No. All elements have a value of 0. Okay. Now, here is a problem that I think you might need to know. Calculate delta H, delta S, and delta G using the following itsy-bitsy data. Okay. For this reaction. So let's do delta H first. Delta H of reaction would be the 2SO3. Here's our delta H. 2SO3, which would be minus the 2SO2